Alright, welcome back. In this video we're going to be talking about several different examples of shear moment diagramming type problems. In particular, things involving linearly distributed loads, hinges on beams, as well as appendages. And so we'll work through a couple of examples. I'm focusing more on how to tackle the problems, more so than maybe the math that are in it. So we're going to do everything symbolically, but you should be able to follow the process. If you have any questions, take a look at the previous shear moment diagram lessons for some tips. So anyway, without further ado, here we go. Okay, so the first one we're going to look at is a linearly distributed load. Okay, and what we mean by that is a load that varies in some amount with its position in X. Now, this particular example, I've started it off at a 0 value here and gone up to a maximum value of W naught, but this could be just as easily, it could have been, some sort of trapezoidal loading where it starts at some non-zero value and then builds its way up. Same process applies to all of these, okay? Now, as you remember when we were looking at the shear moment diagrams of those, if we come in and we look, we know that when we draw our beam and we look at our shear and our moment, we gain an order every time we move down the picture, right? Get a different pencil here so you can kind of see what's going on. All right, so we'd always draw the shear first, we draw the moment second, and then the order of our diagram changes because remember that dm dx is related to v, and that dv dx is related to the load, or something kind of like that. And so we know that since this load is linear, this is an n=1 load, the shear will be second order, the moment will be third order. Okay, so coming up with these areas using the approaches we've outlined before is a little bit of a challenge. So what we're going to do is we're going to kind of come up with an alternative approach. Okay, so like I said, we've got a linear distributed load. We're going to call the length as L. I'm going to work everything off of the left, so that's where my X is being measured from the reference. Okay, and so what we have to do is we have to come up with an equation for this Wx guy. Okay, and so what we know is we know that at X = 0, then my load was equal to 0, and at X = L, my load was equal to W naught. So if I do that, I can plot a line that fits those 2 points as something that looks like this. W naught over L multiplied by its position X will get me the value at any point along this line. Okay, that's just a straight linear function. All right, so first thing we got to do is we got to go through and find our support reactions. So I've done that very quickly. We won't spend any time working on that, but you'll find out that By is W naught L over 3 acting up, and AY is 1/6 W naught L acting up. Okay, and so that will get us our parts. So now we can go in, and so just like before, we draw our shear diagram. I'll try to get on here where we can kind of see stuff. All right, so I know that starting out at a 0 shear, I hit that first point, and it jumps me up to the value of AY, so that's why 1/6 W naught over L is there. Okay, and then we know that because the load is acting down, it's a negative change in the shear, so my next point has to be lower. And it turns out that it goes all the way down to minus W naught L over 3. Okay, so that's the area that happens here, but this is in an n=2 function, and that's an n=2. So finding this area isn't as convenient as working with rectangles or triangles or simple shapes like we did before. We've got to come up with a slightly different strategy to kind of work this. All right, so what we do, the first thing that we have to notice is we notice that we need that point. Remember, that was one of our critical points, that V = 0, because this corresponds to the maximum on the moment. So I have to locate this point, because what's going to happen is the moment diagram is going to increase all the way up to this point, and then it's going to come back down. Okay, now this is simply supported, so I know that I'm going to start out at 0, but we've got to find X max. Okay, and so there's no real easy way to do this other than to go in and write the generalized equations for our picture. All right, and so that's what we're going to do here. Right, so if we draw a generalized equation for this particular shape, for some position at X, we can come up with functions for Mx, Nx, and Vx. This is the power of these equations, is it lets me do some things I couldn't do just with simple geometry like we did before. So if I arbitrarily cut my section at some position X, I pick, and again, take the left half of this, I have my AY here, and then our sign convention for these internals effects that show up is moment is counterclockwise, Nx is tension, and Vx is down positive. That's our sign convention as we defined it last time. And we know that this point, it's still linear. There's a portion of this linear distribution that exists here. So Wx is equal to W naught times X over L. It's that same function, okay? It's just that that's the peak value. So all we're going to do is we know that Vx equals 0 when x is equal to x max. That was the definition that we got here. So all we're going to do is we're going to write the generalized equation for Vx. And we'll do that fairly quickly here. Okay, so I'll warn you, there's a little bit of algebra that's going to come out of this, but it's nothing you guys can't handle. All right, so let's write the equation really quick. All right, so my equation coming off of this picture is that AY is up, so that's a positive. Okay, my Vx is down, so that's a negative, and then I'm going to take the area of this load, which is 1/2 of W naught x over L multiplied by x. Okay, so that's the area, and that's kind of that resultant thing that we were talking about earlier. So that's kind of the resultant of that distributed load, if you will. All right, so if I do that and rearrange my algebra, I get an expression that says that Vx, and again, this is just some algebra, will end up being 1/6 W naught times L minus 3x squared. Okay, so, and that's the equation that we need to be able to work this. So at V equal to 0, I can solve for x in this equation. All right, and so if I do that, all of this stuff goes into the 0, it vanishes, and we're left with L minus 3x squared equals 0. A little bit of algebra. I can say that x is equal to the square root of L divided by 3. Will get me that, and so this becomes the location of x max. All right, so no major problem. Once I have that, then I can go in and I can plug into my equation. So now we want to find out, well, what's this maximum M max value? Okay, and so x equal to x max is equal to the square root of L over 3. We just found that. Okay, so now we can come in. Let's see if I can get this picture back up under here so we can see. A little bit further down. That way we can see it. All right, so all we're going to do then is write the moment equation for this piece. All right, so AY is equal to 1/6 W naught L acting up. This length is x. Okay, so all I'm going to do is I'm going to choose the sum moments right there. And so when I do that, this is the equation I get. I get a positive mx, because the moment's in the direction that I want. Okay, Vx and Nx don't show up in the equation because they're at the point. So they're both multiplied by 0, so I'm not even going to write those. Okay, and then I have this AY guy here that's acting up, causing a clockwise moment, which is negative by our sign convention. And the moment he makes is equal to his AY value multiplied by x. Right? And then we have, well, what is this triangle doing? So we know that we need to come up with some sort of FR times X bar kind of calc to be equal to the moment that that guy makes. So what we're going to do is we're going to do the FR, which is the area under this load. So it's going to be the 1/2 of W naught x over L multiplied by x. Okay, so that's this piece. Okay, and then it's acting at a point. So again, we have a linear load here. That's FR, and we're calling that as x bar. We know that for a linear load or a triangular load, that x bar is going to be equal to, in this case, if it's x long, this is x over 3. Okay, and so that's where this piece here is coming from. So that's the moment that makes, and it's going in a counterclockwise direction, so it's positive also. So again, we're going to do a whole lot of ugly algebra. Okay, and I'm just basically plugging in terms and solving for some things. And so my mx as a function of x looks something kind of like this. 1/6 W naught times xl minus 1/6, and then x cubed over L. And we'll give me that. Okay, and then do a little bit of refactoring, and we should be, I pulled the L's out. Okay, so then all I have to do to find mx, you know, at any value of x is plug in my x values. So the one we're going to be writing is m max. So at that location, we know that m max is equal to mx when x is equal to x max. And that was that square root of L over 3 guy. So again, anywhere that I had an x in this equation, I'm going to plug in the square root of L over 3. And again, a little bit of algebra on here. That's a squared, a little fuzzy. Okay, and we do some algebra, and I end up with an equation that looks like this for the moment. And that's my m max function. All right, so you've got the value of m max, and this is at x equals the square root of L over 3. All right, and that's all there is to it. All right, so what I've done is I've gone and I've redrawn the shear diagram that we had from the previous page. And so all we're doing then is to construct the moment diagram, we can kind of play the same basic games that we did before. This was simply supported, so I know I start at 0, I know I need to end at 0. Okay, and we know that this was n equals 2, this is n equals 2, this is n equals 3, this is now n equals 3, and we have my m max value that's happening here. Okay. Now, normally, if we were worried about all the values in between, we would go through and we would have to plot those. And that worked very well when this was linear or when this was constant. But this n equals 2, this becomes a bit of an issue. So typically, most often in design, I don't worry about what the values in the middle of this thing are doing. I just need that maximum value, because if I design for him, I know I'm going from 0, I know I'm increasing because that's positive. All these other values fall between n max and n equal to 0. So if I design for him, I'm good. All right, now, if we want to kind of get the shape of this, we can play the same game, remembering that dm dx was equal to v. Okay, so we go at this point at x equals 0, because again, we're defining x that way. All right, that my maximum slope is at this location. So this is the most steep slope that I have. It's kind of a positive guy. And then at this case, it's a maximum, so we know that it was 0, and so this shape starts to kind of fit in something kind of like that is my moment diagram. Okay, and that's my m max occurring there. And then likewise, we can play the same game on the other side. Our negative slope, so this is on my steepest negative slope because that value is bigger than this one. And this is kind of horizontal, so this guy starts to do something kind of like that. Okay, now again, we're not really worried about the equation. We have the equation. We had that from up above, right? I mean, here's my equation, and you can see it's an x cubed function acting down, so we know that that's third order, so that matches for what we have happening there, right? And so then I'm just going to quickly call this as positive, and this is positive. All right, so that's kind of how you handle the distributed loads. There's really no easy way to go back and figure out the equations or these areas. Okay, now in some special cases, sometimes you can use those tables that are in the back of your textbooks, that have, like parabolic spandrels, but you have to be really careful on the boundary conditions that are happening here. So in my opinion, it's just easier just to go back to the equations, use those generalized equations that always work, and now I can generate what this picture looks like and figure out what the maximum value is accordingly. All right, so that's our first case, okay, and that's our linearly distributed load. Now, if your load were going the other direction, all you would do is you would modify this function of w of x, and it would be exactly the same, okay? Or if it's part of a bigger beam or whatever, all the other rules still apply. But that's the way you have to go back to generalized equations, by solving where that x max is. That was the trick. Yeah, you've got to be able to find this guy. And that's the whole trick for this particular method. Okay, all right. Let's talk about some other types of beams, okay? In this case, let's talk about beams with hinges in it. So I've got a little bit of an example set up for us, okay? I've solved for the support reactions and worked on pieces, okay? So first thing we have is I have a beam that is simply supported here, okay? It has a hinge in the middle, and then it's fixed at the right end. So this is statically determined. This is actually a frame and machine problem, but I can draw shear and moment diagrams for him as well. All right, and if you recall from frame and machines, the technique is I take everything at a hinge and I blow it apart at the hinges. All right, so I've got a piece 1, which is this guy, and I've got a piece 2, which is this guy. So all I've done is I've got a point load P that's acting a distance A from A and a distance B from the hinge, and then the length of this guy is little c. All right, so if I draw my free body diagrams, I can come in and I can solve for the reactions for, that's my AY. Okay, and it ends up being P times B. And it looks like an A, but it's a B. Okay, all over A plus B, and then over at the other direction, the CY guy that we have happening here is PA over A plus B. And I know it's a little confusing. I got a couple of extra arrows here. Let me get that guy off of there. There we go. Looks something kind of like that. Okay, and then we know that at the hinge, on the opposite side of the hinge, here's my CX, and that's my CY, that this same load is now acting down at this point. Okay, and then that becomes a point load on this cantilever beam, and with that I can go and I can find that my V is now PB, or sorry, that should be a PA. Let me fix that real quick. Okay, PA over A plus B, that's my V, and then PA times C over A plus B becomes my moment. Okay, and notice that it's now in a counterclockwise direction. All right, so all we do then is go back in and start drawing our shear and moment diagram. Okay, so we locate our critical points on here. So if you remember, we'll have a critical point at the support, I'll have a critical point at the load, I'll have a critical point at the hinge, and I'll have a critical point at this other support. So that's what these lines are representing. Okay, so all I do is I go, and again, this is a fairly simple picture, but I want to kind of show you how you put the pieces back together, is that my reaction was PB over A plus B, so that first reaction jumps up. It's constant all the way over to here, okay, and then it jumps down a p-value here, all right? So PB minus P over A plus B will get me to this little reaction value here. Now you'll notice that when I found the reactions on this, that this is PA over A plus B, it was a negative here, okay, just before I got to the hinge. Okay, and so what the diagram says then is that, okay, once I hit the hinge, I'm going to go up by an amount CY. So I go up by an amount CY, okay, but then when I step off the hinge, I immediately come back down that same amount, okay, because it went up CY here, but then it came back down here. All right, so it's minus PA over A plus B, and it's still the same value on the other side of this thing, and it continues on over here. Okay, and then once I get to here, I'm at minus PA over A plus B. I can now be pushed back up by the shear that you had happening there. All right, so a hinge doesn't do anything to the shear diagram, okay, but it does do something to the moment diagram, okay, or it gives you a prescribed value that we'll talk about. All right, so if I go through and I do my moment, okay, and we can solve for all of our values. We start out at M0, and then it's going to be linearly increasing up because it was positive here, and then it's going to come down, and then it's going to come down again, okay, because these are all negative and they're linear. So this is n equals 1, this is n equals 1, and that's also n equals 1. So that's how I know the shapes, okay. And so if things work out, we'll kind of do some proofs here real quick for the moment diagram. All right, so we know that M0 is 0 because that's where we started. Okay, the change between 0 and 1 is this delta M1 value. So that's going to be the area here. So if it's A wide and this is PB over A plus B, then the area or the change is this PAB over A plus B guy. Okay, and that's my change. And so then the M1 data point, which is here, is going to be PAB over A plus B. No major issues. Okay, my M2 then, if you look at it, is going to be this area. And so my value of the shear is PA over A plus B, and this is B wide. So then the area is a negative PAB over A plus B. So what you notice is that the amount that it went up on this was PAB over A plus B. The amount that it's going to come down is that same value. Okay, and so when I do that, notice that the ordinate here, which is my M2 point on here, just using our formulas, M1 plus delta M2 is PAB over A plus B minus that same quantity. That guy's a 0 value. Okay, and so that's one of the properties of a hinge on a frame and machine, is that there is no moment at the hinge location. So anywhere that you have hinges on there, you can almost just put a 0.0 there, or you can use that as a check to know that what you're doing on your mathematics is correct. So we know that that's a 0 value. And then once I get to there, then I can figure out when my next point is lower because I have a negative area on the shear, so my moment's going to be lower as well. Okay, and so the amount that it comes down is now the value of the shear minus PA over A plus B, okay, multiplied by C. Okay, and so that's that quantity. And then the last M3 value then is M2 plus delta M3 is going to be my 0 value that I started at M2 minus this is a minus PAC over A plus B. So that gets me to here. Okay, now you may be asking yourself, well, why am I not back at 0? Well, recall that at that location, which is my C, we had this moment, right? And if you remember the sign convention that we established for concentrated moments, we were going for the left-hand sign convention, which meant that we were calling that as a positive value. Okay, that's an increase. Okay, and so that happens to be in the same direction as my reaction moment, which is a PAC over A plus B. So you can see that when I come in here and I add in plus PAC over a plus b, that will get me back to 0. Okay, and so then we can end up here, and then we step off at 0. All right, so that's what we can look at with these hinge problems. All right, so these more complex sections are kind of interesting, but this is the trick: is if you recognize that the hinge is a 0 value, then you're in business. Okay, I could have almost gone in right off the bat and put it, plugged him in on there. So if you have a beam with multiple hinges, that's your check. If you don't come at 0 on that hinge, you know that you've got a problem in your calculations. So we can work on that. Okay, so that's our hinge, how we handle hinges on our beams. Okay, the last one I want to show you, and this one we won't work all the way through, okay, has to do with what we call appendages. Okay, and these are typical, they're actually fairly common, okay, but these are problems that professors like to put on tests on this, because it kind of makes you understand, two different aspects of it. One, that we're looking at internal forces, but what is the effect of this load? It looks like it's just a single vertical load on this, but if you look, I've got this cantilever appendage here. All right, so what I've done is I've said that the cantilever is located at a distance a from point A, okay, and then it has this extra little e amount, what we'll call is the eccentricity, if you will, and then the point load P acting on this thing. Okay, and so what we do know is we know that cantilevers are statically determinate. So I can always come in, and just like we did with pulleys on our frames and machines, anything that's statically determined, I like to cut it off. Like I said, we're going to cut this guy right at the top here. Okay, so if we do that, the process that we're going to use to analyze this is we're going to remove the appendage. So if I make a free body diagram of the cut piece that I just had, I get a picture that looks like this. All right, so I'm going to put a P load on the end. I have my E eccentricity, and then my unknown support reactions are, I'm going to just draw the cantilever, counterclockwise positive. I'm going to draw the shear, which in this case is a horizontal value. It's not vertical, because again, that's parallel to this cut line. This V cant, then we're just going to draw it arbitrarily that way. And then I'm going to call incant as my normal, and its tension, so I'm going to draw it as acting upward. Okay, so this is statically determined. I can find all three of those values, and that's exactly what I'm going to do here. So if I sum moments at the cut location on here, then my equation is incant positive, okay, minus P times E, because this force multiplied by this E is the moment made about that point. And so I know that the moment at the cantilever is P times E. Okay, and then the sum of forces in the y direction, I know that incant is acting up and P is acting down. This is my equation. So incant is equal to P. And so now I have all of these pieces happening on that. All right, and then just for good measure, sum of forces X equals 0 shows me that the shear is 0 because there's no horizontal load. So that should be no surprise. All right, so now what do I do with it? All I do then is I go in and I basically, because I cut it off and I have to have equilibrium across the cut, here's my cut on this, that the stuff on this side of the cut has to be balanced by the stuff on this side. So here I had an N acting up, so I got to put an N acting down on the beam. All right, and then I have a counterclockwise moment, which is my M cantilever. Okay, it means I got to have a clockwise moment of M cantilever acting on the beam. Okay, and so these will all balance what's happening on that cut. And so what happens is when I do this, like I said, I didn't work this all the way through, but just to kind of show you what happens is the shear diagram should be no surprise, right? That this incant value, it's going to be, some value, and it's going to be constant, and then it's going to drop at that location because of the concentrated load. Right? So that's my minus P, and then it's constant all the way across. So this is an N equals 0. This is an N equals 0 case, which means my linearness shows up on the moment diagram. All right, so this is N equals 1. This is N equals 1. So what this diagram will do is it will start at 0, it increases linearly to some value, okay, and then because of the presence of that cantilever moment, it jumps, okay, and so you get an instant jump from these appendages because of the way that I cut those off. So even though we didn't have a moment up here on this object on the beam directly, it does apply a moment here, okay, because of the way it behaves when I cut this thing off. I mean, imagine this thing's trying to kind of rotate, some amount, rotate in a clockwise direction, okay? And so that's what causes this jump. So it'll jump up the amount of P times E, and then it comes to a new value, and then it will come down based off of whatever your values are. Again, I didn't work all of it out, but that's what's happening, and that's the trick of the appendages. So that if you cut things off, you've got to go through and account for all of the moment, normal, and shear on there, and then just replace it on the beam and then simplify the beam. So you strip this thing down, and now this problem is very, very simple. Okay, and that's the way that we're going to handle these appendages. Okay, so anyway, I hope that that helps. Had some friends that were asking for some different types of examples, so that's what we've done in this. Okay, if you've got any questions or comments, please leave a comment down below and let us know what we can do to help clarify things. And if you like what you see, please like the video, and please remember to subscribe to the channel and tell your friends. That's all we've got for now, so we'll talk to you all later. Thanks. Happy engineering.